So in this video, I want to go into a little bit more about rate laws, just like more in depth, specifically how concentration is affected over time. So recall that for any like non-zero reaction orders, basically the rate itself depends on concentration, and because concentration is going to be depleted, right, as the reaction gets used up, the rate itself will change over time as well. So what that means is that like determining the concentration of a particular reactant at a specific point in time for anything that's a non-zero order reaction can be a little tricky. But there are ways to do it using just some like calculus tricks and things. Now you guys don't actually have to like know the calculus behind this. We're just going to take some equations that have been derived through calculus and use those to help us kind of really finely determine that relationship between concentration and rates of reaction. So for instance, right, if we want to consider maybe a first order reaction, in this case, just like a really generic reaction, reactant A turning into product B, the rate law for this first order reaction would simply be rate equal to K times the concentration of A. Now what we want to do is kind of refine that rate law and give us something that is more robust and more helpful for when we do have, that changing rate over time. And so that brings us to what's called the integrated rate law. So here I have the integrated rate law for a first order reaction in a couple of different formats, right? So on the left, there's one equation, on the right is a second equation. We'll talk about like why these different forms can be helpful for us. But within these equations, right, we see not just the concentration of A, but the concentration of A at certain points in time. So A with the little subscript 0, that indicates the initial concentration, so like the time at 0. And then A with the little t subscript, that indicates the concentration at a specific time, which will signify as just lowercase t. Now, the units of time can vary. It depends really on like what your rate constant units are in, but typically we'll see these time units in seconds, right? That's usually because like our rate constant is in some units involving seconds as well. But so, right, these integrated rate laws are helpful because they involve, not just the concentration, I guess, like at a particular moment, just like once, but they can help us determine the concentration as a reaction progresses, right, over a certain amount of time. We can know how much of our reactant is kind of like left over from that. Now this is again just the first order integrated rate law. We can see here some more examples involving like second or zero order. For a second order reaction, the integrated rate law reads like so. So again, we have like these two formats for it. And again, kind of the derivation behind these is not necessarily important for y'all to know, but just how we can use these, right, is to relate a specific concentration over a certain amount of time. So let's look at an example of maybe how we can apply the integrated rate law right here. So let's say I have this reaction of monatomic iodine, or just I, right, turning into iodine as we like generally know it, right, diatomic I2. And so for this reaction, the rate law is given to the right here. It says that rate is equal to 7.0 times 10 to the 9 per molar per second. And then this is second order in the concentration of I. So right, what I want us to do is use the integrated rate law to determine here the molar concentration of iodine after a certain amount of time. So here we're given an initial concentration of 0.055 molar. We want to find out the concentration just after like 10 seconds of this reaction going on. So go ahead and take a moment to pause, think about how you might solve this, and then I'll show you the answer, and then we'll discuss kind of how I got to that answer. Okay, so hopefully you've taken some time to try to work this one out on your own. What we should find while using this integrated rate law, again, there's like a couple of equations that are relevant here, but for any second order reaction, right, we can use either one of these equations and it'll work just fine. It'll give us the same result. And what I got was B here, 1.4 times 10 to the minus 11 molar. But so let's just be clear on like how we got to this answer. So I'm going to have my math right here on the next next slide. But so again, I have a couple of options here. I can use either of the integrated rate laws that are up at the top. These are the same equation, really, just like rearranged to slightly different means. But in this case, because I am finding the concentration after a certain amount of time, I'm going to go ahead and use the one on the right, just because it's already kind of like set up to find that concentration at time t. And so just plugging in essentially the rate constant, which I have already from the rate law, and then my t here is just 10 seconds, right? Again, it's typically going to be presented in seconds, but just make sure that your units are just matching with whatever the k constant units are. Because that k constant was in per molar per second, I know that that time being in seconds is just going to cancel out the units very nicely. I also have then plus 1 over the initial concentration, so that 0.055 molar comes into play. And so my work is shown right here. I'm first just like evaluating out K times T and then 1 over the initial concentration. And then finally, that gives me then my concentration at time 10 seconds, which is 1.4 times 10 to the minus 11 molar, which seems like a really, really small number, but this reaction goes very quickly, right? Looking at the rate constant, having an order of magnitude of 10 to the 9th power is like really huge. So after just 10 seconds, right, we basically have like none of our original reactant left. It's all been converted into I2 essentially. But so again, this integrated rate law is again super helpful for determining the concentration after a certain amount of time, even though the rate of the reaction changes over time, right? The integration just kind of solves for that and allows us to see that concentration even though the rate is changing. Again, this is an example of a second order reaction. You can see that from the reaction order in the rate law. Also, this integrated rate law is specifically for second orders. We can also see right here for zero order reactions how the integrated rate law would look then. Again, in a zero order reaction, the rate itself doesn't actually depend on concentration at all. And so what that means then is that for the integrated rate law, it's going to look a little bit more simplistic. It's basically either of these two equations, but like because that rate is held constant, whatever change we see to our concentration, that is equal to negative of the k constant times the time. So again, I want us to consider another example here. I have this reaction with this rate law, again, a zero order example. And let's say that I have some of this reactant N2O with an initial concentration of 0.0932 molar. And then we study this reaction over 30 seconds. We find that after 30 seconds, the concentration has dropped down to 0.0905 molar. So my question here is, what would be the rate constant for this reaction, including the units? So go ahead and take, again, another moment to work through this one, and then we'll discuss in just a minute. All right, so hopefully here you've taken some time to work through this example. Again, this time we're trying to solve for the K constant itself. And so what we find is that for this reaction, right, the K constant is going to be equal to 9 times 10 to the minus 5 molar per second. So again, the work for this I'll have shown on the next slide. Again, I can use either one of these integrated rate law equations. I went ahead and went with the one on the left, just because I already know both of my concentrations at these different times, and then I can solve for the K constant there. So setting things up, I have my concentration after 30 seconds minus the concentration initially equal to negative K constant times 30 seconds. And so this works out super easily algebraically. I can solve for K as equal to 9.0 times 10 to the minus 5 molar per second. Again, this is applying the integrated rate law for a zero order reaction. And so we can see that as an example here. Now, I want us to also consider kind of a similar type of problem where instead we're trying to look at like how much time it may take to deplete a reactant. So consider here this example same reaction, so we've got the same rate law, and now we know the rate constant from the previous question. In this case, though, I want us to consider, right, how much time it would take for like 1/2 of our reactant to be consumed. So again, if we initially have like a concentration of 0.0932 molar, then how many seconds would it take for just 1/2 of that N2O to be reacted or to be used up? Again, you can take a moment to kind of think through this, how you would solve for this, and then we'll come back together in just a moment and go over the solution. All right, so in this case, what we're looking at here is how much time it takes. So really solving for t in our different integrated rate law equations. In this situation, we want to set our concentration at time t to just be 1/2 of whatever we started with. All right, so the idea here is that like our concentration initially is 0.0932. The concentration at whatever time we're looking for is just 1/2 of that. So I went ahead and solved for this. I found that that half concentration is 0.0466, right? Again, just the initial divided by 2. And then again, I have my initial concentration given. I have now my K constant from the previous question given. And now here I just need to solve for T, the time. And doing that, I find that time is about equal to 520 seconds. So this 520 seconds, this is referred to as what's called the reaction half-life, or sometimes written just as like a little t with a 1/2 subscript on it. This is essentially like how long it will take for a sample to decompose by half, right, or reach half of its initial reactant concentration. For a zero order reaction, like the one that we saw right here, the half-life can be kind of more quickly calculated using this equation, where we say the half-life is equal to the initial concentration divided by 2K, so divided by 2 times the rate constant. That is effectively what I did in the previous example. This is again just kind of like a derivation from the integrated rate law for zero order reactions. This half-life can be determined. Now for first order reactions, they're similarly going to have like their own half-life. Again, it's a little bit different because the integrated rate laws for first order reactions look different, but the half-life for a first order reaction we can see right here in this equation as half-life equal to the natural log of 2 divided by the K constant. For second order reactions, the half-life is equal to 1 over K times the initial concentration. And so, right, these reaction half-lives are again very helpful for us just in determining, right, how long it will take for a reaction to get basically halfway done. So an example maybe of finding the half-life of a reaction we can do right here, again with this monatomic iodine turning into diatomic iodine example. Let's say, right, we have an initial concentration of monatomic iodine of 0.35 molar, and I want to know what the reaction half-life is for that, let's say in terms of picoseconds, right? Again, this reaction goes very quickly, so I expect it to be a really, really short amount of time for this 1/2 reaction to occur. So setting this one up, again, we want to keep in mind what the reaction order is for the example that we're looking at. In this case, we can see from the rate law that we have I squared there. So this is a second order reaction. And so I'm going to use the half-life equation for second order, which is 1 over the K constant times the initial concentration. So in this case, my K constant is 7.0 times 10 to the power of 9 per molar per second. And then my initial concentration I'm given as 0.35 molar. So I can just evaluate this out. I find that my half-life is equal to 4.082 times 10 to the minus 10 seconds. Again, putting that into picoseconds, if we recall from, I think, Chem 161, but you probably used it a little bit in 162 as well. Pico stands for 10 to the minus 12. So if I want to convert from seconds to picoseconds, I can say 1 picosecond divided by 10 to the minus 12 seconds, right? That works as a conversion factor between those two. And so that means then that fully evaluating this, solving for the picosecond half-life, I get about 410 picoseconds for this iodine reaction described here. Now, again, this is a really, really short amount of time. This happens like in the less than a blink of an eye. And this is expected for when we have such like a large K constant. Reaction half-lives we'll see are really important for situations involving like radioactivity, right? If you've ever played like the Half-Life video games, it's referring to like radiation and how long it takes for, radioactive elements to decompose and become hopefully like less dangerous, right, over time. We'll focus on that a little bit more in like the nuclear chemistry section, but right, this is kind of the same idea behind that going on right here. Now, the last thing that I want to get into with the integrated rate law is, again, going back to like each of those equations that I shown were kind of shown in two different ways. There's a reason for this actually. So one of the formats for each of the integrated rate laws given was written out specifically to resemble a line equation. So the benefit of this is that, if we do have like a lot of data taken from an experiment and we have, all these different rates over time or concentrations measured over time, right, we can plot those in a very specific way to kind of match with those integrated rate laws and help us determine, what kind of reaction we're looking at, that is like what reaction order we have going on. So for instance, if I had like a certain reaction being studied and I measured its concentration over time, and I just plotted that very simply as like concentration on the y-axis, time on the x-axis, and what I find from that data is I get like a nice, neat linear fit. That indicates that I have some kind of zero order reaction. Kind of as confirmation for that, if we look at the zero order integrated rate law, or one of the forms of it, right, we see this linear relationship directly between, say, concentration and time. So although this equation maybe doesn't on its face look like a linear fit, remember that line equations just have the simple format y equals mx plus b, where m is the slope, b is the y-intercept. And so in this format of the zero order integrated rate law, we have again that like y equals mx plus b format that matches with the graph that I have right here, right? We have like y as the concentration at a particular time. We have the slope as essentially the negative rate constant. X is our time. And then b here is that y value at 0, right? The y-intercept is essentially when time is equal to 0 or when x is equal to 0, right? That is our y value, or in this case, our concentration. And so, right, if we do have, this data of concentration and time, which is often, what's measured in kinetic experiments, then we can really simply plot it out. And if it does have this nice linear fit, then that's confirmation that we do have like a zero order reaction on our hands. In the same way, we can do similar things for first and second order reactions. So pictured right here is a plot that would correspond to a first order reaction. Again, the integrated rate law for first order reactions is shown right here as the natural log of our concentration at a particular time equal to negative kT plus the natural log of our initial concentration. And so in this case, right, if we were to plot out not just the concentration versus time, but the natural log of concentration, right, that resembles then the y equals mx plus b format of this first order integrated rate law. And in this scenario right here, our slope is still negative k, but now the y-intercept, that's the natural log of the initial concentration. So again, if we were to plot out our data in this particular way and we got a linear fit, that confirms that we have a first order reaction. And even from that linear fit, we can determine things like the rate constant. We also show like the initial concentration in effect, or the natural log of the initial concentration. And we could predict, say, the concentration at any particular time, right? Just kind of like following this line right here and solving for that unknown concentration. Now, lastly, kind of the same way that we would do this, but for a second order reaction, I've pictured right here. The equation for a second order integrated rate law is shown right here. And then what we would plot in this case is 1 divided by the concentration versus time. And so again, in this scenario, we'd see like a slope that is this time equal to k itself, not just like negative k, again, calling back to what the equation itself was for the integrated rate law. So again, if we were to say take a bunch of data, plot it out as 1 over the concentration versus time, and again, we see this like linear fit, then that tells us that that reaction that we're looking at is indeed second order. It also tells us what the rate constant is in terms of the slope. And so this is a super simple way to just kind of like graphically indicate what reaction order we're looking at. So remember, this is just like one way to determine reaction order. There's also like the method of initial rates that we looked at previously, but this is a super easy, really graphical way, especially when we are, taking our own experiments and measuring the concentration over time for a reaction, right? It's really helpful to use just kind of like this graphical representation, basically plotting out concentration versus time on one graph, maybe natural log of concentration versus time on another graph, and then 1 over the concentration versus time on the third graph. Whichever one of those gives you a linear fit, right, that will correspond to either 0, first, or second order reactions. All right, but so in summary, I have right here just like all of the different rate laws and integrated rate laws, even the units for our different K constants that we might see for 0, first, and second order reactions. This is just like a little helpful summary page. On your formula sheet, you do get, a few of these pieces of information, but definitely keep in mind some of the other ones just as like quick reference for you so that you can easily relate and determine these different 0, first, and second order reactions. All right, but please let me know if you have any questions, and I'm always happy to help. Bye.